Greetings. Good afternoon, good morning, depending on where you are. My name is Professor Duke Orata. We are continuing with our lectures in thermodynamics. Today we want to look at pool boiling, that is heat transfer, boiling points, pool boiling. Consider that you have a pool of a fluid and you have an immersed unit or immersed heating unit in that system. And then you decide to vary the heat flux or the amount of heat which is produced by that immersed surface, and then you keep measuring the changes in temperature at the surface of the fluid and the temperature in the bulk of the fluid. And so basically that's what we are thinking about when you're talking about pool boiling. So we have this fluid and in this fluid we have immersed a heating body. We have a fluid and a heating body, a heating surface is immersed. Like we have said, we now measure the temperature of the surface and the temperature in the bulk of the fluid. Measure the surface, let's call that TS, and bulk temperatures. Call that TB. So measure the temperature at the surface of your fluid and the body of the fluid, what we call the bulk. And of course, you are varying the heat flux in that particular system. So we have that immersed surface, heating surface in that particular pool. Now, what will be the profile? Because remember, it's interesting to determine heat transfer to a boiling system. And we won't delve in that for now. So we just first of all want to look at what should we expect, so that as you advance into those areas, you have gotten the key and fundamental principles which you build on to move into that type of an area. Now, if we take the plot, so if we plot the heat flux versus the temperature change, where theta here is the difference between the surface temperature and the temperature of the bulk. Surface temperature, that's the difference between these two quantities of the bulk. Now, when you draw that profile, let us look at it systematically. You have our profile, log of Q, log of theta. Now, when you have not increased the heat in the system, or you have not increased the heat in the system, you are not heating that particular system, we don't expect any changes in temperature. We don't expect any significant changes in temperature. So basically in that particular system where you are really not heating, or the heat flux is small, we expect most of the movements to be as a result of free convection. So when there is minimum or minimal heat flux, the movement in the fluid will be mostly free convection. So that in that section, basically the movements in the fluid will basically be free convection. So think of that as region A to B. So we have region A to B. Let's call this region A to B. So call that free convection. So most of the movements will be basically free convection. Now, as we increase the heat flux, as we increase the heating of the system, the temperature within the system will increase, and just like in the case of free convection, I need to mention that just in the case of free convection, where we're not heating the system significantly, the heat flux is minimal. If there's any phase change, like evaporation, it will just be normal evaporation at the surface. Note, any phase change is purely evaporation at the surface. And so when we now increase the heat flux, we heat the system up, we're expecting the temperatures to go up, but we're just increasing the heating. Let's say from section B to C. What will happen is that overall, still the bulk of the solution, the bulk of the fluid will not be at the saturation temperature, because you have just increased a little the heat which you are supplying to the system or the heat flux. In section B to C, when we increase the heat flux, because it is not significant, because it is not very significant, the bulk of the solution, will not be at the saturation temperature, It will be at the saturation temperature. And you can see that for both sections A, B, and BC, because the heat flux is not much, not much, not quite significant, then we will not see. First of all, we are not seeing any significant changes in the slope of Q versus T. And number two, even in this particular case, section B to C, as we increase the heat flux, one thing which will happen is that despite the fact that we're increasing the heat flux, we have not increased significantly, such that the temperature of the bulk of the fluid is still not at the saturation temperature. So we just need to note that for section both A, B, and C, note that for both section AB and BC, because the heat flux has not been increased significantly, the slope Q versus theta is relatively constant. But now in section B and C, where we have increased the heat flux reasonably more than in section A to B, we will generate some vapor bubbles. And these vapor bubbles will actually condense when they come into contact with a cold fluid. In section A through C, we will generate vapor bubbles which will condense as they come into contact with the cold fluid. Come into contact with the cold fluid. And in general, for example, in section A through B, you find that in this section A through B, just note again that in section A, B, that section there, Q is proportional to theta raised to power 4/3. So it's about that. It's almost proportional in section AB. Now, as you continue increasing the heat flux in the system, what happens? We will generate more vapor bubbles. We'll generate more vapor bubbles. And of course, they will be moving upwards. As they continue moving upwards, they'll be moving upwards. The more we are there, the surface, the heating surface, there'll be more vapor bubbles generated. So we will expect that there will be a dramatic increase. There will be an increase in the slope. And this increase will continue up to some point which we call D. Now, this portion BC, we refer to this region as subcooled. This is subcooled boiling. There's a subcooled boiling region. So as we now increase the heat flux, you will see a significant change now in the slope, in what we call nucleate boiling. And so you'll be generating more vapor bubbles. They'll be moving up and forth, and as you generate more and more, it will reach a point where now the fluid cannot go back to the surface because of the intensity or the population of these vapor bubbles. In other words, they become an impediment to the fluid moving back to the surface. So the fluid not move back to the surface because there's a tirade of vapor bubbles being released from the heating surface, coming from the heating surface. And so the population of vapor bubbles generated will be so immense that the fluid itself will not be able to get its way back to the surface. And when we reach that particular point, that is point D. Let's write down something first. So as we continue to increase the heat flux, the slope will increase dramatically after state point C. After state point C. And this will continue up to after state point C. The population of vapor bubbles will have increased tremendously, such that the fluid cannot find its way back to the surface. And as this scenario builds up tremendously, we reach a point D. We reach a point D, which we call the critical heat flux. At state point D, we have the critical heat flux. And at that particular point, what happens is that we will have a vapor layer form. A vapor layer form. So at the critical heat flux, that is at state point D, we'll have a vapor layer form. And so there will be a dramatic increase in the temperature of the heating surface. There will be a dramatic increase in the temperature of the heating surface. So I repeat, at state point D, we have the critical heat flux. Remember, we have generated huge populations of vapor bubbles, and now even the fluid cannot get its way back to the surface. And at that particular point, we'll have also formation of a vapor layer, and the heating surface, the temperature of the heating surface will increase dramatically. So there will be a dramatic increase in the temperature of the heating surface. And so remember, we have that vapor layer. And then there's this dramatic increase in the temperature of the heating surface. The heating surface. Go to point E. Let's call that state point E. You have a dramatic increase in the temperature. And at that particular point, that's called the burnout point. And it's a little bit tricky, because if the temperature is extremely high, your heating system will break down. It can melt. You know, the temperature is extremely high. It can melt. So you can find that the temperature at point D, just as an example, the temperature at D, at point D might just be 25 degrees K, but the temperature at point E might be 1000 K. So if you're at 1000 K, that the fact that for your system to hold, that material in the first place has to be special in terms of its thermal properties. So there's a possibility that your system can give way. There will be burnout. There could be burnout, where the heating surface fails or melts. And so if you look at that temperature, there will be a tremendous shift, very big increase in temperature, very big increase in temperature. That particular point. But now, if your system holds. If your system holds, then you will have basically what we call stable boiling. If your system holds, you have what we call stable boiling. But if, for example, you are to reduce the temperature, you will not go back to D directly. You will not go back to D. In fact, you will not go back to D. You will be at some point F. And between D and F, that's a very metastable system. It's a very, very metastable system. In other words, you can be having the vapor layer building up, breaking down, building up, breaking down. So DF is a very metastable system, very metastable section or system. So on lowering temperature, the system we need to write if the system holds, in other words, it doesn't break down or melt, the system holds, we'll have stable boiling. Reducing the heating, the temperature will not go back to D, but rather F. And this region here, D to F, like you've said, is metastable, is unstable. In other words, you could have build-up of the vapor layer, it breaks down and so forth. So it's not very, very stable. The region, DF, is metastable. The vapor layer forming and breaking down. It's a very, that is a very, it's a non-linear behavior. So the vapor layer could be there, it breaks down, so it's a very metastable region. And then of course, do it properly. We'll go back to our nucleate boiling. Let's call this G. Finally, go back to nucleate. To nucleate boiling. So, it is important to mention that it is a challenge because, first of all, we have to look at the formation of these vapor bubbles. We must look at the dynamics of the formation of these vapor bubbles, which is, a lot of it is purely fluid dynamics, so that we are able to understand the behavior of this system. So it's a combination of fluid dynamics and thermodynamics for us to be able to figure out, first of all, how are the formation of these vapor bubbles, for example, their population in terms of population vis-a-vis the heating rate or the heat flux, okay, vis-a-vis the temperature of the bulk and the surface temperature. So it's quite interesting. It's quite interesting is quite interesting and tractable. It's not intractable, it's tractable. And we will come to those at some point. But now, for now, what we want to know is what we have is, if we have pool boiling, we have our immersed heating system there. If you don't generate a lot of heat, or the heat flux is minimal, then most of the movement there will just be by free convection. And as you increase the heating flux, then you have the vapor bubbles, of course, as they are produced, they also condense because they come into contact with the cold fluid, and that we call the subcooled boiling. And then as you continue increasing the heat flux, then we start seeing that there's a change in the slope, that is of heat versus the temperature change. Remembering that temperature change is the difference in the temperature of the surface and of the bulk. And so what are we saying? What we're saying is that it increases, and we reach a point, D, where we're now producing a lot of vapor bubbles. And at that particular point, we call it the critical heat flux. There we have a layer of vapor, and then there will be a sudden increase in temperature at the heating surface. Big increase in temperature, the heating surface. And at that particular point, the heating surface might not hold, depending on the thermal properties of the material itself, which has been used in making that heating surface. And so it might break down or even melt. But if it holds, then you have stable boiling. But now if you decide to reduce the heat flux, you will not move from E to D. No. Direct. No. Move up will be move to F. We will mark that as F. Move to F. And of course, finally, you will be at G, which is the nucleate boiling region. So let's stop at that particular point. We are still looking at these systems.